Coulomb's law, electricity, electrical forces plus quantum mechanics, with one number, one dimensionless constant that measures the strength of the electric force. If you postulate nuclei, their masses are irrelevant, the mass of the electron sets the scale of atoms, and all of chemistry and biology follows. That's a pretty, almost Einsteinian in its grandeur. The next question has to do with one of the foundations, as I just said before, of our modern view of physics. Physics is quantum mechanics. Quantum mechanics is a young concept in physics. It's only been around for 80 years or so. It is still uncomfortable for most people, even physicists who work with it every day of their life. And it is remarkable how many of them believe that quantum mechanics ultimately will fail. At this conference we held a few years ago, there were two Nobel laureates who gave reasons why quantum mechanics should fail, and a famous mathematician, Roger Penrose. I myself am not a conservative, so I think quantum mechanics won't fail in any simple way. Some people believe it will fail for large complex systems. It certainly works. We all believe, well tested at the level of atoms, individual atoms. But maybe if you put together a lot of atoms someplace, it will break down. Tony Leggett, Nobel Prize physics, believes that. Why? I think it has to do with Schrödinger's cat. Anyone who's studied quantum mechanics knows of the Schrödinger cat paradox. In the quantum mechanical theory, in principle, you could create a state which is a superposition of cat alive and cat dead, and it's sort of neither until you do the experiment and observe it, and then it's dead or alive with some probability. It's a very strange business. So far, quantum mechanics, when tested, is proven to be accurate, but maybe it fails for large complex systems. I don't think so, but it's worth testing. Roger Penrose believes that quantum mechanics will fail if we ever, for thought, for consciousness. That's where measurement takes place, and much of the problem with quantum mechanics has to do with thinking about the interaction of observers and observed with consciousness or measurement. I don't think so either. I'm really a reductionist. If quantum mechanics works for atoms and molecules, then it works for the neurons in the brain. Some people believe that quantum mechanics ultimately will fail at very short distances. And there's always been a problem of going to very short distances where gravity becomes a strong force and reconciling Einstein's theory of gravity and quantum mechanics. Gerhard Hooft, another Nobel laureate, believes that that's where quantum mechanics will fail. I don't think so either. I think we have now a theory called string theory in which the two are reconciled, and many of the paradoxes have been resolved. There's one place where I too have worries about the use of quantum mechanics, and that's describing, as I was just a moment ago, trying to describe the whole universe, its birth, its death, the whole thing at once. Then it becomes a bit tricky. But to understand quantum mechanics, we like to be able to do repeated experiments. It's sort of all we can do is calculate probabilities. Or to get outside a system. You can't get outside the universe, and you can't repeat the system. Next question. We have four forces in nature: strong and weak nuclear forces, electromagnetism, and gravity, which I haven't even pictured here. It's such a weak force that presently the energy that we throw, gravity, is totally negligible unless you put lots of protons together to form planets and stars. This is a graph of the strength of the forces versus energy. And with our very precise theory of these these basic forces of nature, we can predict how these forces change with energy. Different energy scales of forces can look differently because of that complicated vacuum, that medium. It can change how the forces behave at different distances. where we got the Nobel Prize. And this is what happens. These forces come together and unify. If you look at very short distances where the energy scales of the particles are very high energy, it appears, according to our theory, which works very well, that these forces all unify. In fact, they, in the best of schemes, unify to better than 1% after extrapolating over 14 orders of magnitude. Happens also to be the place where gravity becomes a strong force. Gravity is a very weak force in the atom. But if you go to very, very short distances, 10 to the minus 32 centimeters, this is a billionth of a billionth of a billionth of a millionth of a centimeter. It's pretty small. There, all the forces would be the same in strength, and they look like they go together. How do they unify? What is the unified theory that Einstein was searching for years and years? Well, we have a direction that some of us have been exploring for years now, which has many of the ingredients we believe to achieve this, but a long way to go. That's called string theory. The next question is it the case that all the particles we observe, all these quarks and electrons, the quanta of light, the quanta of gravity, photons, gravitons, all of the particles that we've observed, the particles that transmit the different forces as well, are they all, as in string theory, different vibrations of a superstring? Could be. I don't have time to say anything more about string theory. That's another whole hour at least. I think we're on the right track. It's an incredibly rich, marvelous subject. And I hope I'm around to see the answer to this question. The next question, too, has to do with the nature with space and time, where we have seen in the last